Hi, and thank you all for subscribing to this session on medical data analysis, part 2, multivariate approach and survival analysis. So as you can see, this is a part 2, which means that there was a part 1, which was a webinar which was hosted yesterday, also on medical data analysis. And in this first webinar, we talked about a small introduction on how to analyze medical data. My name is Jean-Paul Maalouf. I'm a data science consultant at the ExcelStat software. ExcelStat will be used to illustrate this webinar. I will try to be as intuitive as I can in my speeches, and I try to avoid as much as I can reference to complex mathematics. You should know that we're going to see a few popular analysis tools, and notably multivariate analysis tools typically used in medical research, such as logistic regression, linear regression, and survival analysis. But unfortunately, in 1 hour, we won't have the time to go in depth to investigate each of these methods. If you want to learn more about them, please don't hesitate to request a consultancy or a training from the ExcelStat team, and we'll be more than happy to organize something for you, which will be tailored to your questions and needs. You can download the handouts of the presentation as well as the data I will be using to illustrate the webinar. So there's a download button somewhere on the webinar platform. At the end of the webinar, there will be a Q&A session. So please don't hesitate to submit your questions in the chatting box. Okay, you can submit them anytime during the webinar. I'll take as much time as I can at the end of the webinar to answer as many questions as I can. What are we going to see today? I'm going to first start by saying who we are, what we've seen in the last webinar yesterday. Yesterday, we've seen methods that are simply univariate. We've investigated, for instance, the effect of one single risk factor or one single independent variable on one single dependent variable, such as, for instance, the effect of treatment administration, drug versus control, on recovery or on systolic blood pressure, for instance. So this was the effect of just one single independent variable. Today, we'll see models that investigate simultaneously the effects of several independent variables on some clinical outcomes. We will see what's the advantage of going multivariate first. Then we'll see how to investigate the effects of several variables on quantitative outcomes, and we'll be talking about multiple linear regression. The effects of several variables on qualitative outcomes, we'll be talking about logistic regression. Then I'll introduce you to survival analysis, which allows modeling survival and hazards or time to events according to several variables. This is the case of Cox proportional hazards. I will show you two mainstream statistical analysis used in survival analysis, Kaplan-Meier analysis and Cox proportional hazards. So a few words on ExcelStat. ExcelStat is a statistical software that works as an add-on to Excel on PC and on Mac. It's also available for Excel 365 and Google Sheets. So if you'd like to use it on the cloud, it's also possible. In a few numbers, ExcelStat has more than 220 statistical features, more than 150K users worldwide, more than 25 employees, more than 300K monthly visits on the website, and the software is available in 7 different languages. And we have offices in 3 different time zones, America, Europe, and Japan. There are 10K monthly downloads of the software. ExcelStat is developed by the Addinsoft company, which is hosted by the Data Factory. The Data Factory is a private lab dedicated to data science and based in Bordeaux in France. Data Factory also hosts 4 other expert companies which work around data. It organizes more than 25 workshops, events, and trainings every year, also around data science. ExcelStat is a statistical software available in 8 solutions to meet your specific needs. There are 3 generalist solutions, which are Basic and Basic Plus and Premium. With Basic, you get the basic data analysis tools such as statistical testing or tools for statistical modeling such as regression or ANOVA or logistic regression, and tools for clustering such as AHC, and also methods for data preparation, visualization, and cleaning. Basic Plus will add machine learning to these methods, machine learning that are used for prediction. And Premium has the complete set of 220 ExcelStat features. And between Basic Plus and Premium, you get these intermediate solutions, which are more field-oriented. So today we'll be focusing on methods that are included in all the solutions, except for two methods we'll be seeing today, which are survival analysis methods, so Cox proportional hazards and Kaplan-Meier analysis. These two methods are included in the life sciences solution, as well as in the premium solution, of course. ExcelStat has an extensive set of resources available for free online. Each statistical feature in ExcelStat is linked to a specific tutorial, which guides you through the analysis from a short explanation on how the feature works to the configuration of the ExcelStat dialog box and the interpretation of results. ExcelStat also develops a YouTube channel called Stat Cafe. In Stat Cafe, you will find several videos, each video corresponding to the functioning of one specific feature and an illustration using the ExcelStat software. So the explanations are quite intuitive, and it's a good introduction to these several statistical features. You also have free webinar recordings available online. So there's been a set of webinars on general statistics. So a webinar on data description, another one on data exploration and clustering, one on statistical testing, statistical modeling, ANOVA, and supervised machine learning. So what have we seen yesterday? Here's a short summary. What is a study design first? A study design is a set of methods and procedures used to collect and analyze data in the framework of a particular research problem or a particular research question. In medical research, study designs include cross-sectional studies, cohort studies, case control studies, and clinical trials. Maybe some of you are already familiar with some of these designs. Then, what is a variable? You will see I'll be using this word quite often today, and I used it quite often yesterday also. A variable is a measurable element which can take different values. There are roughly two global types of variables. Qualitative variables, which we also call categorical. Qualitative variables cannot be expressed in terms of numbers. They cannot be quantified. They include the gender, for instance, so male versus female, the presence or the absence of a disease, or the occurrence or the non-occurrence of a disease, a treatment administration, drug A versus B versus placebo. And then the second family of variables is quantitative or numeric variables, such as renal clearance, weight, systolic blood pressure. These variables can be quantified. They can be expressed in numbers. Now, in medical research, we usually investigate the relationship between two categories of variables, two classes of variables, independent and dependent. Usually, we try to study the effect of independent variables or of risk factors on dependent variables, which are clinical outcomes, such as disease or relapse or recovery. So independent variables are the variables whose effects on the outcome is being studied, and they include, for instance, age, sex, cholesterol, weight, smoking habits, drug administration. So some of these independent variables can be totally controlled, such as drug administration. So this is typical of clinical trials. And other independent variables are more inherent to the patients, and they cannot be as such controlled, such as age, sex, cholesterol, weight, and so on. The dependent variables or outcome variables are the variables that develop or that change or that evolve or that are affected by independent variables. For instance, disease, survival, systolic blood pressure, time to disease, and so on. So as you can see, in both independent and dependent variables, you have both types of variables. Look, in independent variables, age, cholesterol, weight are quantitative, whereas sex, smoking habits, drug administration are qualitative. Now, in dependent variables, you also have qualitative variables such as disease, yes, no, survival, yes, no. And otherwise, you also have quantitative variables such as systolic blood pressure. You can also have time to disease variables, which are some kind of a quantitative variable, but which will be treated in a different way, as we will see at the end of this webinar. So time to disease or time to death, this kind of variables will be investigated in the framework of survival analysis. But anyway, according to the types of independent and dependent variables, you have several statistical methods that allow you to investigate the influence of independent on the dependent. Here is how a typical data set in medical research looks like. In this case, you have a case control study. Incident cases of leprosy in a region of North Malawi were compared with population controls. So we sampled cases of leprosy in northern Malawi, which we compared to a sample of healthy patients. So here in rows, we have one patient per row. And in this column, we have the outcome variable, which indicates whether the patient is a case or a control, or whether the patient has the disease or is healthy. In between, you have these independent variables: age, sex, vaccine scar, school, house type. And the purpose will be to investigate the effect of these variables on the outcome. And these variables can be either quantitative or qualitative. In this case, exceptionally, they're all qualitative. So the summary of the last webinar. In summary, I showed you an analysis process suggestion. So first, describe and clean your data well. Descriptive statistics allow to pinpoint some errors or some abnormalities in your data and to clean them, to correct them, or maybe to transform some variables to make them more appropriate for analysis. This is the first advantage of data description. Second advantage is that description also shows you some trends or what to expect from the second step in the analysis. The second step being assessing the effect of the independent variable on the outcome. So the description step is very important. Today I will be neglecting it a little bit just to have time to go through some specific analysis, but it doesn't mean that it's not an important step. Please pay attention to the step, it's very important. Then the tests and models we've seen. We used student t-test to assess the effect of a qualitative variable on a quantitative outcome, Fisher's exact test to test the effect of one qualitative variable on one qualitative variable, and simple linear regression for the effect of one quantitative over another quantitative. I showed you this guide, which will help you choose mainstream statistical methods for data description according to the situation, and then mainstream statistical methods for risk factor assessment. So here, for instance, according to the independent variables you have and the dependent variables you have several statistical methods available, and I included examples within the table. And this guide is a wrapper of 3 available guides online: statistical testing, modeling, and survival analysis. Okay. So yesterday we've seen these 3 cases. We investigated these 3 cases. Today we'll be investigating the remainder. Now, a small reminder before moving on how to interpret the outcome of a statistical test. It's very important for you at least to have one first way of interpreting p-values for those of you who don't know yet how to interpret a p-value. So what is a statistical test? First, a statistical test is statistical method, which allows answering a question whose answer is yes or no. For instance, is average of A significantly different from average of B? Statistical tests involve two hypotheses, the null hypothesis as well as the alternative hypothesis. The null hypothesis generally implies an idea of equality, so mean A equals mean B. The alternative hypothesis, an idea of a difference, mean A is different from mean B. Now the statistical test will produce a number called a p-value, which is confined between 0 and 1. And the lower the p-value, the more significant is the effect. The lower the p-value, the more significant is the difference between mean A and mean B. Usually you compare your p-value to a risk threshold alpha, which is often set at 0.05, but you really need to think strategically where to set alpha before running the study. Very often we set it at 0.05. That's not a reason to do it systematically. So if the p-value is lower than alpha, you reject H0 and accept HA, assuming a risk proportional to the p-value of being wrong. Okay. Now, the three exciting things we'll be seeing today: going multivariate Y, modeling binary outcomes, this is recovery or recovery yes no with logistic regression, and modeling time to event data using survival analysis. So first, going multivariate Y. What's the interest of going multivariate? Do you remember yesterday, for those of you who were attending yesterday, we investigated this data set, which was made up, in which 15 smokers undergoing a specific surgery in the near future are compared to 15 non-smokers undergoing the same surgery. So see in this column, you have the smoking status of the patients, which are in rows. And then the surgery success score is measured after the surgery of all of these patients. This is the dependent variable. And these are the independent variables, all of these variables. So smoking status, and then some physiological variable A, another physiological variable B measured in each patient. So each of these variables may potentially influence the outcome. Last time we asked this question, does physiological variable B influence surgery success score? So this is quantitative versus quantitative, as you can see. We used simple linear regression model, which can be written as such, so y equals a plus bx, to test the effect of the x variable on the y variable, or independent on dependent. The simple linear regression model can be represented by line like this. And if we write it down once again using real variable names, we get this: success score equals a plus b multiplied by this variable. So this is the dependent variable, which we also call y, and this is the independent variable, which we also call x, and a and b are the model parameters or coefficients. Now a is the intercept, so this is the intersection between the model line and the y-axis, and b is the coefficient which we most of the time are interested in. This is the slope of the line. So if b is negative, it means that the line is decreasing. If b is positive, it means that the line is increasing. If b equals 0, then the line is flat. So the software will compute estimates of these parameters and will allow us to see whether the line is significantly increasing or decreasing. And each time you run a statistical model, such as linear regression model, you capture a part of the reality, but there is a part of reality you are unable to capture. And this part of reality is represented by all the distances between the points and the model, so which are represented in red arrows here. These are called the residuals or the errors. So what we're unable to capture with our model. The result in ExcelStat looked like this. So part of the result looked like this. We have this table, which is the model parameters table. Each row corresponds to one coefficient in the linear regression equation. So this is A and this is B. These are parameter estimation or coefficient estimations. And these are p-values, which are associated to the parameters with null hypothesis and alternative hypothesis. So as you can see, both p-values are very low. which means that in both cases we can reject the null hypothesis and accept the alternative hypothesis. So practically speaking, success score significantly decreases with physiological variable B. How can I say this? The associated coefficient is negative, as you can see, and significantly different from 0 as shown by the p-value. So we were expecting anyway that this coefficient would be negative as the slope was negative on the chart. So, okay, we investigated the effect of physiological variable B on surgery success score. How about the other independent variables? How about smoking? Does smoking affect success score? Does physiological variable A also affect surgery success score? So what we could do maybe is to test the effect of this column on this one through a student's t-test, for instance. And then separately, we assess the effect of this column on this one using a simple linear regression. So we'll have 3 separate studies to assess the different effects we have. But this is a problem. Why running a separate analysis for each independent variable is a problem? Well, imagine this situation. You have a model with only one independent variable. Here we are univariate. We only have one independent variable. You have the outcome here. And for instance, the physiological variable A. You can say the outcome is the surgery success rate. In this case, what can we say about this relationship? Physiological variable A has a negative effect on outcome. So far, everything's fine. Now imagine this second situation. What happens when adding another variable, such as smoking status, in the model? Now we are multivariate. We are investigating simultaneous effects of 2 variables on the outcome. Imagine you have this situation. You have an outcome, still the same points. It's exactly the same data, but I colored the data according to the smoking status. You have non-smokers at the top and smokers at the bottom. Now let us assess the effect of physiological variable A on the outcome within each group. We get a positive relationship, which is very contradictory to the first analysis, but closer to reality. So physiological variable A has a positive effect on outcome once we take into account another variable. So in multivariate analysis, independent variables are adjusted to one another, which brings you a bit closer to what's really happening in reality. So I will take one first example of multivariate analysis, and I will run multiple linear regression. What is multiple linear regression? This is a method that helps investigate the linear influence of several explanatory independent variables on the dependent variable, which is quantitative. Okay, so instead of having y equals a plus bx, we have y equals a plus bx1 plus cx2 plus dx3. x1, x2, and x3 are 3 different variables. There are a few warnings, a few things you should really be careful about when running multivariate modeling like this. In addition to the assumptions about residuals we had already seen yesterday around linear regression, beware of 2 things in multivariate modeling: overfitting and multicollinearity. Unfortunately, I won't have the time to go into these details. If you want to learn more about these, don't hesitate to check the webinar recording on statistical modeling. You have a link here, okay? There's an additional constraint. The number of explanatory variables or of independent variables cannot be higher than the number of observations. So the number of independent variables cannot be higher than the number of patients. Otherwise, the classic multiple linear regression won't work. But there are other techniques, which I won't be talking about today, which are adapted to these particular situations. So the question is now, which of the 3 independent variables in the rectangle here mostly influence surgery success score? We're going to run multiple linear regression. So I'm going back to ExcelStat, modeling data, linear regression. So this is a typical ExcelStat dialog box. And in ExcelStat modeling dialog boxes, you always have in the general tab fields to fill out the dependent variables and fields to fill out the independent variables. Here we have surgery success score as a dependent variable, so I can select it directly in my Excel file like this. And for the dependent variables, I'm going to select physiological variable A and physiological variable B. And I can select smoker as a qualitative independent variable. I click OK when I'm ready. And I'm going to go down to the analysis of results, the model parameters. So we still have the same kind of tables with one row per coefficient and coefficient estimates right here, which are associated to p-values. Now, first thing I'm going to check here is the p-values. We only have one variable which is associated to a significant p-values. The other variables are insignificant. The only variable which is significant is physiological variable B once again, and it's still linked to a negative coefficient. How do we interpret this? If all the other variables were held constant, an increase in physiological variable B by 1 unit results in a decrease of success score by 1.76. This is how you interpret the coefficient of a multiple linear regression. Now, how about multivariate models for qualitative outcomes such as case control or recovery, yes, no? So far, today at least, we've investigated only a dependent variable which is quantitative. We're going to move on to a dependent variable which is qualitative. Let's talk about logistic regression. And you are very specifically in this situation here. We have many independent variables and we want to study their impacts on a qualitative outcome. I'm going to take a case control example with logistic regression. I'm going to be working on this case control of leprosy, cases of leprosy in the region of northern Malawi, which I told you about a bit earlier. We have one outcome which is qualitative, 0 and 1, and independent variables. Now, the thing we could think of by looking at these data is that the case control column is coded in numeric values, 0 and 1. So we could be tempted by launching a classic multiple regression and interpreting coefficients. But this is wrong. I will tell you why. Why we can't use classic linear regression in this situation. A linear regression model is valid only under certain conditions, which are linked to the assumptions about residuals. And these conditions include the dependent variable should be numeric and continuous. Dependent variable should not be bounded or confined between two values. So here the dependent variable is not continuous. It can only take two values, which are 0 and 1. So you cannot run linear regression. So the following slide includes an attempt to build a simple linear regression anyway out of the data. Look, I plotted a scatter plot of my outcome, so control versus cases, zeros versus ones, according to some independent variables. So you have blue dots at the bottom and blue dots at the top, and I built a classic linear regression within these data. So the outcome equals A plus B multiplied by the independent variable. What's the problem in this? Simple linear model, the first issue is that the dependent variable is not continuous. So it can only take two values, 0 and 1. One solution would be to work on the probability that y equals 1 instead. In other words, on the probability that the patient is a case or the patient is diseased. So instead of working on 0 and 1 data, we can work on the probability that the patient has a disease, which is 1 minus the probability that the patient is healthy. So we have a continuous variable here, as the probability can take an infinity of values, but the problem is that the probability is bounded between 0 and 1. So we still have a problem. We still cannot use linear modeling classically. So one solution in this case is to remove the bounds of the probability by using a link function, which we call the logit function. So instead of working on the probability, we work on the logit of the probability, which equals the linear equation, which we already know. So more on this on the following slides. So in summary, we make the data continuous by working on the probability instead of the binary outcomes, and then we remove the bounds of the probability by using a link function, which is called the logit function. So here I'm taking my model back, the last model I've written here, the logit of a probability of being a case equals a plus b multiplied by the independent variable. How to develop this thing here? Like this. This is the logarithm of p divided by 1 minus p. This is the probability of being a case. And this is what we call an odds ratio, which we'll be interpreting in the outcomes of logistic regression. Now, if you can see, whenever the p gets close to 1, the probability p gets close to 1, this quantity gets close to positive infinity. Whenever p gets close to 0, this quantity gets close to minus infinity. So we removed the bounds of the probability. We can transform this data to get the values in terms of probability, which is a bit sometimes more intuitive to interpret than the log of an odds ratio. And this gives a chart that looks like this. You have a probability of disease according to the independent variable. You have a smooth probability in orange like this, which goes from 0 to 1 according to the independent variable. So the higher the values of the independent variables, the higher the probability of having a disease. I'm going to launch a logistic regression on my data in ExcelStat right here. So I'm going to use modeling data logistic regression. So in the general tab, I will take case control. All my variables are qualitative. Then in my missing data, I'm asked to remove the observations because as you can see, there are missing data here. I'll just click OK. I get my result as usual in a new Excel spreadsheet. So I will go down to one of the most interesting tables, which is here. Once again, the model parameters or the coefficients. Now it's much bigger than the one we've already seen because we have many levels within each qualitative variable. Now, how can we interpret this? So this is one of the most delicate parts of the webinar. I'm going to focus on just one variable, which is the vaccine scar. Let us focus only on the interpretation of this independent variable. The interpretation of the others is similar in practice. So usually when you model qualitative variables statistically, the statistical software will set a baseline level for this qualitative variable. And in this case, the software chose scar no, level no, as a baseline. And all the other levels will be compared to this baseline. This is the case of yes. I'm going to give you one first interpretation of this coefficient, this yes coefficient here, one first interpretation which is easy. Then I'll give you another interpretation which is a bit more technical, okay? So the easy interpretation, when switching from not having a scar to having one, so from no to yes, the odds of being a case or of being diseased decreases because the coefficient is negative, as you can see. So the odds of being a case will decrease. And this is significant, as you can see, by the p-value. Now, how can you interpret specifically this value here? What does this 1.062 mean? You need to check the odds ratio here. The odds ratio, which is the exponent of this coefficient. All the other variables held constant. When having a scar, this ratio, so probability of being a case divided by the probability of being healthy, will decrease by a factor of 0.346. In other words, the odds of being a case to the odds of being healthy is multiplied by 0.346 when you have a scar. So far, we've seen both qualitative and quantitative outcomes. So multiple linear regression for quantitative, logistic regression for qualitative. How about time to event outcomes, time for survival analysis, which is the last case we're going to investigate today. Introduction to survival analysis. What is survival analysis? Survival analysis helps analyzing time elapsed until an event occurs, or time to event. And this event could be death, for instance, which is very classically analyzed with survival analysis. It could be also relapse, it could be recovery, it could be the appearance or the occurrence of a disease. And typically you get this kind of curves that shows survival probability according to time elapsed. And you can compare several curves corresponding to several groups of patients. In this case, we have one control group in green and one drug group in red. If I focus on the red survival curve, and I take, for instance, the 10th week, I can say that at the 10th week, I have around 0.8 survival rate. So 80% of chance of surviving until day number 10. So you can compare the curves here, and you can see, for instance, that people who took the drug have a better survival across time as compared to controls. There are two things you can estimate in survival analysis. The survival function, which is what you're seeing in this chart. This is the probability that an event hasn't occurred yet at time t. And the hazard function, which is the rate at which a patient is likely to undergo the event at a specific time t. So the hazard function is more instantaneous. The survival function is more on the duration. So some methods allow investigating the effects of independent variables on survival or hazards. And in survival analysis jargon, independent variables are often called covariate. Here are two examples, a clinical trial example, like the example we've seen in this chart. What is the effect of a new drug on relapse probability? A group of patients is giving the drug, and another one receives a placebo, and the time to relapse is recorded for all patients. This is a cohort analysis example. What risk factors influence hazards for an event? Risks include age, gender, and health history. Now, there's a very important idea you should be aware of in survival analysis. This is censorship. We often miss information on event dates for some patients. Here are examples. Patients who abandoned follow-up during the study. Sometimes we just don't know when the event occurred for this or that patient after the patient has left the study. Then you can also have patients who did not undergo the event before the end of the study, if we're studying time to death. If some patients did not pass away before the end of the study, we do not really know the time until their death. So this is what we call right censored data. We know that the patients survived until a certain time, but we don't know what happened after, how much time they needed to undergo the event. Censored patients are not excluded from the study. Survival up to a certain time is always interesting information, which is taken into account by survival analysis methods. Okay, so this is right censored data. You should know that there are other types of censored data, such as left censored or interval censored. For left censored data, we don't know precisely the date of the start of the study, for instance, the start of the treatment for this patient or the occurrence of a disease for this patient. If we're studying, for instance, the time to death since the occurrence of a disease. So this is left censored. But most of the time, investigate right censored data. How do we collect the data now? You have a start and an end of the study along a time frame. Each line here corresponds to the follow-up of one specific patient. The orange dash means that the monitoring starts for this patient. It means, for instance, that the disease appears or the treatment is administered, and we are following up the patient until the event happens. So the event occurs at the end of the arrow here. For some other patients, we have censorship. to the right. So patient lost follow-up before study period has ended. So for these patients here, we lost follow-up. We know that they survived until a certain time, but then we don't know what happened after. And for other patients, they did not undergo the event by the end of the study. So these are all censored patients. How survival analysis datasets are usually structured. You have one patient per row, as usual. You have the time to the event. This is the arrow length in the previous slide. So the arrow length corresponds to the time interval until the event. Then you have a column indicating whether the event has occurred or whether the patient is censored. And you also have independent variables, which are called covariates in survival analysis jargon. There are many analysis methods in survival analysis, like life table, Kaplan-Meier, Nelson-Allen, cumulative incidence. They all have their advantages or their pros and their cons, their specificities. And some of them allow introducing the effect of independent variables, others don't. Today we're going to see Kaplan-Meier and Cox proportional hazards, which are the most commonly used methods in this context. I'll start with Kaplan-Meier analysis. So this is one of the most popular methods used to estimate survival functions over time. It is a non-parametric method. It does not rely on probability distribution, so it's very robust analysis. Practically, Kaplan-Meier function estimates the probability that a patient will survive past a specific time t. It's possible to use a log-rank test to compare survival curves of two groups, for instance, drugs versus placebo in clinical trials. We're going to be able to test the null hypothesis that survival curve for group 1 equals survival curve for group 2. So the alternative hypothesis will be survival for group 1 will be different from survival curve from group 2. However, the problem in Kaplan-Meier analysis is that it does not allow for quantitative independent variables or for multivariate modeling. So for this, we're going to use Cox proportional hazards instead. But Cox proportional hazards is slightly less robust than Kaplan-Meier analysis, as it's not completely non-parametric, whereas Kaplan-Meier is completely non-parametric. Now, the question we ask, survival time of patients suffering from advanced lung cancer was followed in the North Central Cancer Treatment Group. We have several covariates recorded, the gender, which is qualitative, age, which is quantitative, and ECOG performance status, which measures how well the patient can perform usual daily activities. The higher the ECOG performance status, the worse the situation is. Some patients are right censored, as you will see in the following slide. Question, does gender induce a difference in survival curves? So for now, we're only going to test the effect of one independent variable, which is gender. This is the data. We have the time elapse in days until death, since the beginning of the illness and until death. We have the status column. Did the event occur at the end of this period or not? And at last, we have independent variables. So I'm going to launch my Kaplan-Meier analysis on the data right here. So Kaplan-Meier analysis is part of the survival analysis menu in ExcelStat, which is part of the life sciences solution and the premium solution. There it is. In all survival analysis methods in ExcelStat, you will be able to specify the time here, as well as the status indicator right here. And of course, you need to indicate which code corresponds to the event and which code corresponds to the censored data. In the data options tab, I'm going to ask for a by group analysis. I want to compare group. I want to compare genders. Okay. So I click OK. So one of the first nice things in Kaplan-Meier analysis we get is this big table here, big detailed table, which I'm going to comment on the presentation. We get one for each group. Here, this is the table for males. Let us focus on time 53. So we have different time dates. At time equals 53, we had 128 surviving patients, among which 2 passed away. So we had 128 patients who were still alive before t equals 53, and 2 passed away at t equals 53. And this is 1.6%. So 2 divided by 128. Survival rate corresponds to 1 minus this value. Then this is the survival distribution. This is what is estimated by Kaplan-Meier analysis. So after t equals 53 and until t equals 54, 91.3% of patients are still alive. So survival rate until this time is 91.3%. And of course, this distribution is bounded between 2 confidence interval bounds. Then you get this nice chart in ExcelStat, which compares the 2 survival curves, so for males and for females. As you can see, for the F group, females group, we have a better survival globally, maybe until a certain time, until 700 days, for instance. And the bubbles you see here correspond to censored data. You need to know that in the report, there are many other things that are estimated. For instance, for the males, you can see the mean survival time. Okay, and you can see also quantiles. So at 25%, 50%, and 75%. You have the same for the females, mean survival time, which is much higher. Then let me get back here. ExcelStat also provides this test of equality of the survival distribution functions associated to a p-value. The p-value is lower than alpha. We can reject the null hypothesis that the 2 survival curves are overlap. And we can say that the 2 survival curves are significantly different. So what if we wanted to go multivariate and include the remaining independent variables in the analysis? Cox proportional hazards model will allow us to do so. So Cox proportional hazards model describes the probability of an event if the subject survived to a specific time t. In some way, it measures the instantaneous risk of the event occurring at time t, and this is the definition of a hazard. It has one big advantage over Kaplan-Meier analysis, as it allows for the inclusion of several independent variables in the model. So we're able to run multivariate modeling using Cox proportional hazards. This is how we write down a Cox model. This is the hazard at time t. So for instance, the risk of death at time t, which is equal to a baseline hazard, a baseline risk of death, which is influenced by covariates associated to coefficients. So B1 and B2 are coefficients of the covariates. When a coefficient is higher than 0, the corresponding covariate increases hazard and thus decreases survival length. So when coefficients are positive, this means that the corresponding covariates have a significant effect on hazard and thus on the risk of death. So I take back the same data set and I ask another question. Which covariate mostly influences hazard rate? I'm going to launch my Cox proportional hazards model using the survival analysis menu. There it is. So I select once again my time data, the status indicator, and at last the explanatory variables. I'm going to take age and ECOG performance as quantitative variables, and the gender as a qualitative variable. So these are the independent variables. I click OK. Once again, if I go down in the report, I get a table with different coefficients here and associated p-values. So these are coefficient estimates with associated p-values. Let me focus first on ECOG, which is positive and significant. Holding all the other variables constant, ECOG performance has significant positive impact on hazard or on risk of death. So the higher the ECOG performance, the higher the risk of death. Coefficient is positive and the p-value is significant. It's the same thing for gender, which I remind you is a qualitative variable. So 0.552 is the difference in coefficient between M and F. So when you switch from F to M, you increase the hazard, and this is significant. So holding all the other variables constant, being a male also significantly increases hazard. And to interpret this coefficient more specifically, we can take the hazard ratio, which is right here, which is the exponent of this value. It equals 1.737. So being a male increases hazard by 74%. So you should be careful because Cox proportional hazards has assumptions. So one of the most important assumptions in Cox proportional hazards lies in its name. The ratio of the hazards for any two individuals is constant over time. In other words, covariate effects remain constant across time. If this is not respected, then your model won't be reliable. So how to test for these assumptions? So for qualitative covariates with a few levels, such as gender, you can use Kaplan-Meier curves, and they should globally remain parallel across time. So they should look like this for gender, F and M. You see, they are parallel across time. If you have something like this or something like this, the assumption is violated. Another way to check for this assumption is to have a look at the proportionality test for each covariate as well as for the global model. And this is provided by Exelstat. Looks like this. So each variable and the global model is associated to a proportionality test p-value. When a covariate is linked to a proportionality test p-value lower than alpha, then proportionality assumption for this covariate is violated. If you place alpha at 0.05, the assumption is never violated in our case. So to sum up, in statistical modeling, the multivariate approach, as we saw, gives more accurate results than the univariate approach, as independent variables are adjusted to one another. Logistic regression helps modeling qualitative outcomes, and it's based on the logit transform. Survival analysis helps analyzing time to event data, such as time to recovery or time to relapse, time of death. We saw two survival analysis features, Kaplan-Meier, which is a non-parametric approach for estimating and visualizing survival curves and allowing to test the influence of qualitative independent variables on survival. If you want to evaluate the simultaneous effects of several independent variables on time to event, use Cox proportional hazards, which allows for multivariate modeling, but which has assumptions to check. So we've investigated all of these cases during these two webinars. I really hope you enjoyed, and we hope this will be useful. If you want to go further in your analysis, or if you have some further questions, or if you need any other training or consultancy, please don't hesitate to contact Exelstat. We'll be very happy to adjust something for you. Don't hesitate to join us on the social networks. Thank you very much for attending, and I wish you a very good day. Bye-bye.